So, and I guess the other detail that, just for those of you who are in the room, that we worked out was that the session chairs won't be going to the podium. We'll invite you from our seats. So I'd like to begin our first session, which is on sources of particulate matter. And I've said enough about the nature of the sources in my overall introductory remark. We're concerned, of course, with particles penetrating from outdoors, and then also with particles that originate from indoor sources. And I'm really pleased with the panel of three speakers that we've recruited to help summarize the state of knowledge and the research challenges and practical knowledge challenges that we face in this area. Brent Stevens, our first speaker, is not so long ago graduated from the University of Texas at Austin, and is an assistant professor at Illinois Institute of Technology, where he runs the Built Environment Research Group. So Brent, please give us your presentation.
Thanks for the introduction, Bill, and for the broader introduction to the entire workshop. It's a real honor to be kicking off this workshop and the activities. And what I'm going to go into is a little bit of a little bit more detail on what Bill has already introduced in that very fine introduction. And so I was charged with two very different tasks. The first one was describing what we know and where we're going with understanding how outdoor air contributes to indoor PM exposures. That's something that I research actively. And also, don't forget, there are indoor emission sources, some of which are combustion, some of which are non-combustion. So we've done some work in this area as well. So I've got this sort of split talk between outdoor air, which we'll start with in the beginning, and then a little bit on some non-combustion appliances as indoor sources of PM towards the end. So I just want to start with a quick sort of review of indoor exposures to outdoor PM, and let's start with what we know, or at least what we think we know. First off, we know a lot about outdoor PM exposure and associations with adverse health effects, right? So we know documented health effects include stroke, heart disease, lung cancer, chronic and acute respiratory diseases, including asthma, lung function, mortality, and so on. And these are associated with a number of measures of PM that have already been introduced: PM10, PM 2.5, to mass-based measures, to a lesser extent ultrafine particles, or the number concentration of particles less than 100 nanometers, and various chemical components of these various PM measures as well. Some of these are causal, some of these are suggestive, and everything in between. So we know a lot about these associations that have been made with outdoor PM and adverse health effects. We know enough that in 2012, study by EPA, some EPA researchers estimated about 130,000 deaths were attributed to elevated outdoor PM 2.5 in the US in 2005, and we've got enough outdoor PM 2.5 data to understand differences in mortality, spatial differences in mortality around the US. So we know this pretty well. But, and I thought I was going to be the first person to get to say this, but Bill already beat me to it. Maybe we'll hear this in number of speakers today also. But what happens is we spend most of our time indoors, nearly 90% of the time on average, almost 70% of our time at home. So residential exposures are very important. We also know that outdoor PM enters into buildings with varying efficiencies, so outdoor PM becomes indoor PM. At the end of the day, as Bill highlighted, human exposure to outdoor PM often occurs indoors and really often at home, and I'll provide several references for many of these things. So it's important to think about the actual sources of outdoor PM into buildings, and it's pretty simple. It's pretty straightforward. This is a figure from a paper in 2011. It's one of the best reviews that I've seen or the most comprehensive reviews I've seen of indoor-outdoor relationships for particulate matter. So we've got outdoor particles outdoors that enter into the indoor environment through cracks and gaps in the building envelope. That's through air infiltration. We introduce outdoor particles indoors through natural ventilation. That's open windows. And outdoor particles are also introduced by mechanical ventilation. So while this looks like a home, drawing of a home, this is fairly applicable to all types of buildings. Commercial buildings will have better or different filtration and more mechanical ventilation, and in general less natural and/or infiltration. And then we've also got indoor particle sources as well. So that's sort of the simplistic view of looking at these things, and that's about all you need to know to start. We can define a couple of terms that are key to think about as well. The first one is simply the indoor-outdoor ratio. This is a concentration of indoor particulate matter relative to the concentration outdoors. So that includes both indoor and outdoor sources. And then there's another term called the infiltration factor that we've got to be familiar with. And this is the indoor-outdoor ratio of particulate matter in the absence of any indoor sources. So it's a number between 0 and 1. 1 is high, 0 is none. So let's start with a review of indoor-outdoor PM ratios. So this includes indoor and outdoor sources. And this is one of the most comprehensive summaries that I've seen, again, from this 2011 paper, of the indoor-outdoor ratio from very large studies across the world. What they're plotting here are 4 different PM categories. On the left, we've got PM 2.5, and we'll start there. And each one of these bars is the average from over almost 80 studies in over 4,000 homes of simple indoor and outdoor ratios. So that includes both indoor and outdoor sources. If you look, the median average indoor-outdoor ratio for PM 2.5 is right here, right around 1. Right, but that's a mixture of both indoor and outdoor sources. If you move to PM10, larger particle sizes, you've got a little bit lower median average indoor-outdoor ratio of about 0.8, and similar ratio for ultrafine particles, or a measure that's close to ultrafine particles, close enough. So that gives us some rules of thumb to start with. On average, in most buildings, the indoor particle concentration for PM 2.5 is roughly the same as outdoors, but that's a mixture of indoor and outdoor sources, and there's also a lot of variability from top to bottom. So moving forward into looking at outdoor PM sources alone, this same paper reviewed infiltration factors. So again, a number from 0 to 1. These are means from about 20 samples of what they considered large samples for those that have measured infiltration factors. Large meaning over 20 homes. That's not that large, but it's large. That's all this field has. So this includes only outdoor PM infiltration. The total number of homes is about 1,000 homes in the United States, maybe 150 or so in Europe. Homes in Europe are in the white bars. Homes in the US are in the gray bars. And we know we have most data for PM 2.5. You can see most of these studies focus on PM 2.5, less for PM 10. But if we look at the median average infiltration factor for PM 2.5, you get at the number Bill suggested, around 50% or so, 55, somewhere between 50 and 60%. And variability from about 0.3 up to about 0.8, depending on these studies, which vary in location, they vary in human behaviors in those buildings, and they vary in season as well. PM10, larger particles penetrate through the building envelope less efficiently. You've got lower infiltration factors. A general rule of thumb for an average, say, about 0.3. And the same goes for infiltration factors for ultrafine particles. I'm not showing the data here just for time, but in general, you look at a bunch of studies in homes in the US and Canada and other places, you're looking at a typical indoor or an infiltration factor for ultrafine particles of about 30%. But what's really interesting to me is within each one of these bars, you've got considerable variability. So not just on average across the building stock and across different places in the world, but also within each one of these bars, you've got a lot of home-to-home variability, which Bill also introduced. So I just wanted to provide some data here on variability and infiltration factors to help motivate us a little bit. If we start on the top left, we've got distributions of infiltration factors that were measured in a 2010 study of ultrafine particles in homes in Windsor, Ontario, in the summer. And we've highlighted here sort of the minimum and the maximum weekly values of infiltration factors. You've got down in the bottom left here, less than 0.1. So almost no indoor exposures to outdoor PM in that building, in that particular home. And in the top right here, you've got almost one. So almost complete exposures, indoor exposure to outdoor PM, and everything in between. Luckily, things are reasonably tightly bunched around that magic number of 0.3 or so, but sort of not so much. There's a good 25% or a third or so of the homes are outside of that band. Same sort of thing for infiltration factors for PM 2.5 in Edmonton, Alberta, reported in a study a couple years ago. These are measurements in the winter. I'm just picking a few here and there. Similar distributions, PM 2.5 infiltration factors as low as less than 0.1, so less than 10%, and as high as almost 100%. Now, what's going on is there's some key drivers of this variability, which we'll talk about in a second. And if we look in the US for infiltration factors for PM 2.5 across 7 cities in another recent study, and these were made using gravimetric measurements, these were made using optical measurements, so there's some variation there. These require some different estimation methods. But essentially, you're looking at a similar range, not quite as big, but from as low of across all cities, as low as about 0.3 and as high as about a 0.9 or so. So the long and short of this is that we have large between-home variations from less than about 10% to about 100%, the indoor proportion of outdoor particles or the infiltration factor. And it varies home to home, it's pretty consistent across the types of particulate matter sizes and classes that we've seen characterized. So what are some of these key drivers of variability? And these are things that we know quite well. The first is the source of ventilation air, right? So if you've got outdoor air primarily coming in through infiltration, through leaks, versus mechanical ventilation with and without filtration, versus natural ventilation or open windows. That's pretty straightforward. Speaking of open windows, we know, therefore, that human behaviors, such as window opening frequencies, is a really big driver of variability in infiltration factors. Another driver is the magnitude of the air exchange rate, whether that's based on infiltration or mechanical ventilation or natural ventilation, some of which is driven by meteorological conditions. So these drive variability. We also know that we have variability in infiltration factors depending on sizes and classes and even components of PM, although there's some data needs there as well. And we also know that building characteristics such as air tightness, even the age of home, and HVAC system design and operation can all drive this variability in infiltration factors. So that's something that we're curious about in our research group, and it's understanding mechanistic drivers of these things. So now let's get into what we don't know about indoor exposures to outdoor PM, or at least what we know less about is probably the fairer statement. The first is, how does variability in infiltration factors contribute to effect estimates or health effect estimates in epidemiology studies? And there's a few people in this room that have done about the only work in this area. So I'm highlighting just 3 studies just for time here, but I really don't know of that much more. So there's been at least a few efforts to account for variations in air exchange rates between buildings or between communities, and to some extent even window opening, in the underlying epidemiology exposure estimates. One of the first was done by Charlie Weschler and colleagues and published in 2012, where they generated, they were looking at PM10 and mortality across the US. And what happens is you see in the epidemiology literature, you see these variations in the rates of mortality based on location and even seasonal differences. So what they did is build or construct this PM10 exposure coefficient, which essentially tries to account for the likely variations in air exchange rates across the different parts of the US based on housing characteristics and climate conditions and window opening behaviors and HVAC runtime, and also different seasons in those same locations. They came up with this exposure coefficient and found that it was reasonably well correlated with the mortality coefficients that were derived from epidemiology studies. So this really said, wait a second, if you try to account for the underlying indoor exposure to outdoor PM10 based on some key drivers of variability, you can explain a lot of the differences in mortality coefficients that were observed. That's my best summary of your work. I hope I did all right on that. So interesting, really helpful work. And then Natasha Hodas in 2013 and colleagues also took a similar approach looking at PM 2.5, outdoor PM 2.5 and acute myocardial infarction in New Jersey, and split homes in the region into low, medium, and high air exchange rate homes based on housing characteristics and other things, and found a higher odds ratio in these homes with higher air exchange rates that would thus have higher indoor proportions of outdoor PM. So using epi data, reconstructing underlying exposure estimates, and finding these patterns. Another one in 2013, looking at PM 2.5 and emergency room visits in Atlanta, to some extent also stratified indoor exposures to outdoor PM 2.5 by air exchange rate categories, and to some extent found stronger relative risks of PM 2.5 and ER visits in these higher air exchange rate categories, but not consistent across the board. So there's not a lot we know here. This is about all we've got. I maybe have missed some, but accounting for variability and infiltration factors and understanding how they contribute to health endpoints is something that we really don't have a lot of information on. The next one, the sort of elephant in the room: how often do people open their windows, and what is the impact of that on air exchange rates? You couldn't ask a simpler question, really, in this room, but we don't have a lot of data. We have a lot of pilot study data, like Johnson and Long 2005, who surveyed about frequency of window openings in residences in North Carolina. You know, they found about 25–30% of the time people had their windows open. Pilot study, single location. Similar pilot study here on the left, Price and Sherman, an LBL report in 2006, which the authors sort of also state we're a little leery of some of this data. But essentially, they surveyed people as well and came up with the cumulative distribution of how often people in California open their windows a large amount, or a medium amount, or a low amount. And in the winter, found that about 50% of the population didn't open their windows at all. And then the other 50% had a wide distribution. And in the spring, a lot more open windows. But that's phone surveys in California, pretty limited data set. Despite the limited data, we in our group and Charlie in his previous effort, we've tried to piece these things together to kind of model what we think distributions of window opening might be. So there's been some work there. Even if you can get to that point, how do air exchange rates vary with open windows? There's been a lot of case studies on individual buildings. There's been some larger field study efforts, i.e. 1 or 2 homes, that have found how air exchange rates increase with different window opening strategies, and have come up with some rule of thumb sort of air exchange rate multipliers. Sorry, it's down on the bottom of the slide here. And typically 2 to 4 times higher when windows are open, but define windows being open, define indoor-outdoor temperature differences in meteorological driving conditions like wind speed and direction. So there's a lot of data that we don't have on window opening frequencies and the impact on air exchange rates, let alone outdoor pollutant infiltration. And then another key missing or data need or key set of research questions we have relates to the underlying mechanisms that govern infiltration factors for outdoor particles. So if we look at this simple schematic, outdoor particles enter into the indoor environment. We've already described the infiltration factor, but we can describe a few more terms that drive the infiltration factor. And that is, first off, the penetration factor through the building envelope, or this parameter P. The air exchange rate, we've already mentioned. The product of those two tells us the rate at which outdoor particles are delivered. And then you have removal by air exchange rate and other loss terms that include deposition to surfaces, phase changes for some constituents, control by filters or air cleaners, and so forth. So if we just focus on this one parameter, P, the penetration factor, if you're not familiar with it in this room, it's another, we love numbers between 0 and 1. It's another number between 0 and 1, where 1 essentially means that all outdoor particles penetrate through the building envelope or any openings in the building 100% efficiently, so the envelope offers no protection. And then if P is equal to 0, the envelope offers complete protection. The envelope or the shell of the building is a perfect filter. So what do we know about penetration factors in buildings for different sizes and classes of particulate matter? We know mechanistically a lot from a 2001 study by Bill and a graduate student that did a modeling effort of typical cracks and building envelope constructions and defined this penetration factor and got us to understand kind of what the underlying physics between these or the underlying physics in this parameter. One of the main things that they produced was that the penetration factor is highly size resolved, so highly dependent on particle size. About 10 years later, in this same review from Chen and Zhao in 2011, this is a review of essentially all the knowledge on size-resolved measurements of size-resolved penetration factors in buildings across the world. We're talking about less than 20 buildings, and that's being a little bit conservative, probably 12 or 15 buildings or so. And we know we've got this sort of characteristic upside down U shape of penetration factors where these mid-sized particles around 0.3 microns or so tend to penetrate more efficiently than larger and smaller particles. And again, this is from 10 nanometers to 10 micrometers. But problem is you've got a lot of uncertainty, a lot of scatter. You also have some studies that only use, ultrafine instrumentation. Some use larger. Very few have sort of used the whole spectrum. So we just don't have a lot of data on size-resolved penetration factors. The same time this study came out, another one by Dongyin Rem and Lance Wallace at NIST at the time sort of came up with a new way to measure penetration factors for ultrafine particles. They extended the range down from 100 nanometers down to 10, down to almost 5 nanometers. So we've got almost 5 nanometers to 10 micrometers that have been characterized in a few buildings. Great, low uncertainty. Problem was it took 2 days to take this measurement in an unoccupied house. You can't do it in real homes unless you're working with a realtor in vacant lots, right, or vacant homes. So it's a challenge. We published in 2012 with Jeff Siegel when I was at UT Austin a sort of broader suite of measurements of just ultrafine particle penetration factors in homes in Texas, almost 19 homes in Austin, Texas, and we came up with a sort of quicker test method for doing so. But the problem is it's not as deep. There's no size resolution. It's just total ultrafine particles. But we saw high variability from top to bottom and some influence of building characteristics. So my base summary of this is that this is a really important parameter that governs indoor exposures to outdoor PM, and it's a size-resolved basis, and does so on a size-resolved basis. But the number of homes with penetration factors that have been measured in the entire world, size-resolved particles, something like less than 20 homes. Ultrafine particles as a category, something like 30 to 50 homes, depending on how you count it. And then for PM 2.5, the class that we know the most about from an outdoor standpoint, it's actually really it's been estimated in hundreds of homes, and we use those data, but they've seldom actually been measured in a sense. They're challenging measures to get at. I say seldom measured. I don't know if I've ever actually seen a measurement in the classic way of a PM 2.5 penetration factor in a home. So a lot of data needs there. There are some other unknowns or less unknowns that I don't have too much time to go into, but associations between infiltration factors or penetration factors and building characteristics. There's some associations of associations with air conditioner usage, year of construction, envelope tightness. We're working on our group trying to measure how this changes after buildings undergo retrofits. Chemical transformations, people are working on that, so I'll leave that for others. And then one thing that we just don't have is high spatial and temporal resolution data for things like outdoor particle size distributions and outdoor size resolved aerosol composition. We just don't have this data, so even our modeling efforts are challenging. So our quick summary of outdoor to indoor PM transport research needs. We need more integration between epidemiologists and exposure scientists, and that should probably say building scientists and indoor air scientists as well, so we can address exposure misclassification that some suggest occurs for not accounting for indoor transport of outdoor PM. And to improve health effect estimates. We need more data simply on window opening frequencies that impact and their impact on air exchange rates. And I think we need more data on field measurements of size resolved, ultrafine particle, and PM 2.5 penetration factors. So I left exactly 1 minute to talk about indoor sources, because there's a lot of people talking about indoor sources here. Other than me, and I'm looking at just non-combustion appliances. So a total shift in thinking to some extent. So we know that there's several non-combustion appliances that emit indoors, and the next two speakers will talk more about indoor emissions. So this is why this is just a short tag here. Most of these are in the ultrafine particle range, but you'll hear some more nuance there. We know that activities and devices, and I call these appliances, but that might not be the exact right word. Vacuum cleaner bags. We know that using vacuum cleaners emit particles, many in the ultrafine size range. We know ironing with steam emit particles mostly in the ultrafine size range. We know that laser printers emit particles largely in the ultrafine size range. And now more recently, we know that things like desktop 3D printers, which essentially melt plastic onto a heated base plate, emit ultrafine particles as well. So what's really important here that I just want to leave with is that it's one thing to know that something emits particles, it's another to know the emission rate. So it's really important to get emission rates. We just published another study on desktop 3D printers and both particle and VOC emissions. We basically found that UFP emission rates, because we did chamber testing, we could back calculate these things to a reasonable certainty, vary anywhere between about 10 to the 8 to about 10 to the 12 particles, ultrafine particles per minute. So we're talking about hundreds of billions of particles per minute is the order of magnitude of some of these things. And then the last one I want to mention is we're sort of, and I mention these because we keep finding every once in a while new sources of indoor PM, just when we thought we had it sort of figured out. Some new finding from Lance Wallace and some of his colleagues are heated surfaces. Bill mentioned this as well. And I'm just showing some data that I borrowed from Lance from his conference presentation last fall at the International Society for Exposure Science. And he basically did this experiment where he was seeing ultrafine particles, very tiny particles, even sub 10 nanometers, coming off of heated surfaces. So he was wondering where was this coming from. So he would wash these pans, get them clean, leave these pans out for particle deposition to occur from the indoor environment, absorption of SVOCs to the surfaces as well. Then he would heat the pans, and sure enough, he'd get particle production in the red here. When they had been exposed to the indoor environment for longer and you heated them, you got more ultrafine particles coming off. And then when you covered and didn't allow any exposure to the indoor air, you really didn't get any particle generation. So my summary here is that I've done sort of an incomplete literature review of ultrafine particle emissions from a lot of different indoor emission sources that are non-combustion. Basically, you've got anywhere from 10 to the 8 to 10 to the 12 particles per minute from lots of different sources that are non-combustion. We continue to find new sources of indoor PM, and we need to continue to gather emission rate data for these and other sources, including size-resolved emission rate data, because that is often lacking. And essentially, we also need to continue to explore source control and exposure mitigation strategies. And I'll end there. Thank you.
Thank you, Brent. More than admirable job to an impossible task. I gave you the responsibility for giving 2 full talks in 20 minutes.